Did you know that right now, all around you, there's this invisible storm? It's a frenzy of waves carrying music, messages, and all the data that powers our modern world. And in this explainer, we're going to make them visible. I mean, have you ever really, truly stopped to think about it? You tap your screen, and a photo just appears on a friend's phone on the other side of the country. What is actually happening there? What is physically moving through the air to make that possible?
Well, it's not magic. It's physics. It's the really elegant science of invisible waves. So for the next few minutes, we're going to pull back the curtain and show you how this hidden world really ticks.
Okay, so to understand how these signals work, we first have to learn their language. Every single wave has a kind of DNA, 3 core properties that engineers can tweak to encode and send information. First up is amplitude. The easiest way to think about this is just as the wave's strength or its power. A tall wave has a high amplitude and it carries more energy. A short wave has a low amplitude. It's literally the difference between a whisper and a shout.
And you've seen this in action with AM radio. The AM literally stands for amplitude modulation. To get music to your car, the radio station simply changes the wave's height, its amplitude, to perfectly copy the original sound wave. Next, we have frequency. This one is all about speed. How many times a wave cycles up and down in a single second? We measure this in hertz. A low-frequency wave is kind of slow and stretched out, while a high-frequency wave is super fast and all bunched together. And this brings us to that classic trade-off, right? AM versus FM radio. AM waves can go the distance. They actually bounce off the atmosphere, which lets you hear a station from hundreds of kilometers away. But FM, which stands for frequency modulation, gives you that much clearer, crisper sound because its waves travel in straight lines, though they can get blocked by things like mountains. Now, our last property is a little more abstract, but trust me, it is the key to our entire digital world. It's called phase. Imagine you could just freeze a wave mid-cycle. Its phase is simply its position at that exact moment. Is it at a peak, a trough, or somewhere in between? By deliberately shifting that starting point, we can encode digital information. This technique, it's called phase shift keying, and it's what your smartphone is doing all day, every single day. When you send a message, your phone is translating the ones and zeros of your data into these tiny, precise shifts in a radio wave's phase, and then it beams that code to the nearest cell tower. Pretty incredible. So now that we have the ABCs covered, we can zoom out and see the bigger picture. Let's take a little tour of the electromagnetic spectrum, this huge, invisible rainbow of energy that all these waves belong to.
And here it is, the whole shebang, laid out by frequency. We're going to take a journey from the long, gentle waves on the low-energy side all the way up to the short, super powerful waves on the high-energy end. Each part of the spectrum tells a totally different story about our universe and the technology we've built with it.
Down here on the low-energy end, we've got radio waves. Their long wavelengths are perfect for blanketing huge areas, which is why we use them for radio broadcasts in our 4G and 5G mobile networks. And right next door are microwaves, which are fantastic at carrying massive amounts of data in a focused beam. This is the tech behind your Wi-Fi router and the entire GPS system.
Moving up in energy, we hit infrared. You use this every day with your TV remote, but it's also the light that carries data through fiber optic cables at unbelievable speeds. And this really shows you just how little our eyes can perceive. Right next to infrared is this tiny, tiny little sliver called visible light. That is the only part of this entire vast spectrum that we can actually see. Beyond what we can see, the energy levels get intense. Ultraviolet or UV waves from the sun are powerful enough to cause a sunburn. X-rays are even more powerful, passing right through skin and muscle to let doctors see our bones. And at the very top, you have gamma rays, the most energetic waves of all, which we've actually harnessed in medicine to destroy cancer cells.
Okay, so we have the waves, we know their properties, but how do we make them talk? How do we stick our music and photos and messages onto them? Well, it turns out there are 2 fundamental languages for this: analog and digital.
Analog is a smooth, continuous wave that's basically a direct copy of the information it's carrying. Just think of a vinyl record. The groove is a physical replica of the sound wave. It's beautiful, but it's also fragile and can get noisy. Digital, on the other hand, is completely different. It speaks a super simple language of just 2 states, on or off, 1 or 0.
This simple binary language is the bedrock of all modern technology.
Because it only has two states, it's incredibly robust and easy to correct for errors and interference. Every photo you take, every song you stream, is just a massive string of these ones and zeros, encoded onto waves with perfect clarity. So let's put it all together. When you combine the properties of waves, the electromagnetic spectrum, and digital signals, what you get is the invisible architecture of our modern world.
I mean, think about this. Right now, satellites are orbiting 20,000 kilometers above you, beaming down these incredibly precise microwave signals. Your phone is catching these faint whispers from multiple satellites just to calculate your exact location on the planet. And for that to even work, the clocks on those satellites are so precise, they actually have to account for Einstein's theory of relativity. It is an absolutely extraordinary feat of physics.
This is it. This is the invisible language that shapes our reality. From the analog grooves on a record to the digital pulses that guide a GPS, the physics of waves connects and empowers us in countless ways. So next time you send a text or stream a movie, maybe you'll see it a bit differently. You can now visualize the hidden world of signals all around you. So, what piece of everyday technology now seems the most amazing to you?
All right, let's dive into something you do every single second you're awake, but probably never really think about. How do you see? I mean, how does the world out there get in here into your head? Well, the answer is this incredible journey through the science of optics. It's the story of how light travels from an object to your eye and then gets transformed into a thought.
No, really, just pause for a second and think about that. That chair across the room or the screen you're looking at right now, how do they make that leap from being physical things to being a picture inside your mind? It honestly feels like magic, but it's not. It's pure physics.
And this is basically our roadmap for today. This whole amazing journey of light, from an object all the way to your brain, really just boils down to two key things: how light bounces and how light bends, before our own amazing biology takes over. So let's follow that path step by step.
Okay, first up, the first thing light does when it hits pretty much anything in the world is it bounces. We call this reflection. And what's so cool about it is that this entire complex-seeming process is governed by one single, beautifully simple rule.
It's this simple. The angle that light hits a surface is always the exact same angle it bounces off at. That's it. That one law explains everything, from the reflection you see in the mirror every morning to the super sophisticated radar systems that can track an airplane from miles away. So think about a normal flat mirror. The image you see isn't actually on the glass, right? It looks like it's behind it. It's upright, but it's also perfectly flipped, which is why when you raise your right hand, your reflection raises its left. What's happening is your brain is tracing those bouncing light rays backwards in a straight line to a point where it thinks they came from. Now this is where it gets really fun, when you start to curve the mirror. If you curve it inward, kind of like a bowl, you get a concave mirror. It gathers light and focuses it to a single point. That's why a magnifying mirror can zoom right in on your face, and why a car headlight can create such a powerful focused beam. But if you curve it outward, you get the opposite, a convex mirror. It spreads the light out, giving you that super wide fisheye view you see in security mirrors at a convenience store or on your car's side mirror.
Okay, so that's bouncing. But what happens when light doesn't bounce off something, but actually passes through it? You know, like going from the air into a glass of water. Well, that's when light literally gets bent out of shape. And this is the magic of refraction.
You've seen this a million times. You stick a perfectly straight straw in a glass of water, and all of a sudden it looks like it's bent right at the surface. It's not an optical illusion. Well, not in the way you think. Your eyes aren't playing tricks on you. The light itself is actually bending. So why does it bend? Well, it's all explained by something called Snell's law. And really, it just comes down to one thing: speed. Believe it or not, light actually travels slower in water than it does in air. So as it hits that boundary and suddenly slows down, it pivots, it bends. This is the exact same reason a fish in a pond always looks like it's closer to the surface than it really is, and it's why spearfishing is so incredibly difficult.
And of course, once we figured out how to bend light, we started shaping glass to do it on purpose. That's how we get lenses. A convex lens, the kind that's thicker in the middle, focuses light. That's what you need to correct for long-sightedness. On the other hand, a concave lens, which is thinner in the middle, spreads light out, and that's exactly what someone who is short-sighted needs.
So how do opticians actually measure the power of a lens? They use this unit called a diopter, and the formula is beautifully simple. The power is just 1 divided by the lens's focal length in meters. That's just the distance it takes for the lens to focus light down to a single sharp point.
So if we put that all together, when you see a prescription from your optometrist that looks something like this, you now know exactly what's going on. That negative number, that's your clue that it's a diverging concave lens. It's designed specifically to help a short-sighted person see things far away more clearly. It's the physics of refraction, totally personalized for your eyes.
Now, if you take this whole idea of refraction and you push it to its absolute limit, you get something incredible called total internal reflection. Here's the deal. If light is moving through something dense, like glass, and it hits the edge at a really, really shallow angle, it literally can't escape. It can't bend its way out. Instead, it reflects perfectly back inside. This is the mind-blowing principle that makes fiber optics work, trapping a beam of light so it can bounce its way for miles and miles to deliver your internet.
So we've covered how light bounces and how it bends. Now let's talk about the grand finale. Let's look at the ultimate optical instrument, the one that uses all these principles to literally build your reality, the human eye. Just look at this number for a second, 80%.
That's right. 80% of all the information you process about the world around you comes directly through your eyes. It is, by a massive, staggering margin, our most dominant sense. It's not even close. And the way it works is just this incredible feat of natural engineering. So first, light from the world enters your eye. Then, the eye's flexible lens, which is a natural convex lens, bends and focuses that light onto the retina at the very back. And finally, the cells in your retina act like tiny translators, converting that light into electrical signals that your brain can finally actually understand.
Now, don't get me wrong, our other senses are absolutely vital, right? Hearing is the foundation of our language. Smell is deeply, mysteriously linked to our memory. And of course, taste and touch are crucial for our survival. But when it comes to the sheer volume of data our brain is crunching about the outside world, sight is just in a league of its own.
And that brings us to one final, kind of mind-bending idea. We followed this whole journey, from a simple ray of light all the way to a complex thought. But what does that really mean for how we perceive reality itself?
You see, what this all means is that we never actually experience the world directly. Our brains are always building a model of reality based on the sensory data it gets. The light waves hitting your eye don't have any color, the vibrations hitting your eardrum have no sound, color, sound, these are creations of your mind. Which leaves us with this one profound question. What is the universe actually like, totally separate from the senses we use to interpret it? Kinda makes you wonder, doesn't it?
Have you ever just stopped and thought about the magic happening inside the device you're watching this on right now? I mean, it's this little pocket-sized universe we carry around every single day, but most of us don't really get how it works. Well, over the next few minutes, we're going to pull back the curtain and demystify the tech that powers our world, all the way from its 19th century origins right up to your fingertips.
Okay, let's kick things off with a fact that just sounds, well, impossible. The phone in your hand, right now, has more raw computing power than all of NASA's computers combined when they first put a man on the moon. Just let that sink in for a second. It's an absolutely mind-boggling leap, and it really sets the stage for everything we're about to unpack.
Right? How is that even possible? How did we manage to go from computers the size of a room to supercomputers that we can literally lose in our couch cushions? The answer is an incredible story of physics, really clever engineering, and some truly mind-bending miniaturization. So, our journey starts at the most fundamental level you can get, the language that every single digital device speaks. And no, it's not English or Mandarin. It's something way, way simpler. It's called binary code, and it's a language with just two letters, a 0 for off and a 1 for on. That's it. Every photo you take, every message you send, every video you watch is, at its very core, just an incredibly long, complex sequence of these ones and zeros. And when I say long, I mean astronomical. To put it in perspective, just 1 hour of 4K video is made up of about 400 billion ones and zeros. So how in the world does a machine actually read and process that massive amount of code? Well, that brings us to the physical heart of the digital world. Meet the unsung hero of the modern age, the transistor. The easiest way to think about it is as a microscopic light switch. It can be turned on to represent a 1 or off to represent a 0. These tiny, tiny switches are the physical building blocks that process all that binary code, and their size is almost impossible to wrap your head around. This incredible shrinking act is what we call Moore's Law. Get this, the very first transistor back in 1947 was big enough to hold in your palm. Today, a processor chip smaller than your fingernail holds over 10 billion of them. Each one of those little switches is literally smaller than a virus. That's how your phone got so incredibly powerful. All right, so we have these unbelievably powerful chips, but they're pretty useless if they can't talk to each other, right? The next piece of this giant puzzle is connecting them all in a vast global network. So let's take a look at what I like to call the world's digital plumbing. Ever wonder how an email can zip from Oslo to Tokyo in less than a second? It uses a system called TCP/IP, and the best way to picture it is as a digital postal service. It takes your data, let's say it's a photo of your cat, chops it up into tiny little parcels called packets, puts an address on each one, and sends them out into the world, where they get perfectly put back together on the other side. Now, these packets travel on a really complex system of digital roads. Your home Wi-Fi, that's a local area network, or LAN. Think of it as the neighborhood streets. But when you go to a website, you're connecting to the wide area network, or WAN. That's the interstate highway system. And the internet? Well, it's simply the biggest WAN of them all, connecting everything everywhere. And this is where you start to see the true scale of it all. We're talking about a massive, interconnected web of undersea fiber optic cables that carry data as pulses of light, cellular towers beaming signals through the air, and countless routers directing traffic every single millisecond. It's a global machine, and it's working 24/7 to keep all of us connected. But none of this modern magic just appeared out of thin air. It was all built on the brilliant discoveries of scientific giants from more than a century ago. So let's meet some of the pioneers whose work made everything we just talked about even possible. It really all started back in the 1860s with a guy named James Clerk Maxwell, who, just using math on paper, predicted that invisible electromagnetic waves had to exist. Then, about 20 years later, Heinrich Hertz proved he was right by actually producing and detecting those waves in his lab. And then, in 1901, Guglielmo Marconi took that pure science and turned it into world-changing technology by sending the first wireless signal clear across the Atlantic Ocean. It's this perfect chain from pure theory to global impact. And here's a fantastic little historical footnote for you. After discovering these world-changing waves, Hertz himself said they would be of no use whatsoever. It's just a powerful reminder that even the most brilliant minds can't always predict the future that they're helping to create. Okay, so let's reel it all back into today, to us. Because this entire system, from that tiny transistor all the way up to the global network, has fundamentally reshaped our daily lives, our society, and, even our own minds. And this brings us to a huge question. How are so many of these online services free? Well, as this table shows, there's always a transaction happening. Every time you search for something, like a post or share a photo, you are building a highly detailed data profile about yourself. That profile is then used to sell incredibly targeted advertising. In a very real sense, you aren't the customer. Your attention is the product that's being sold. Now, with so much of our lives online, security is absolutely critical. And one of the simplest, most powerful tools you can use is two-factor authentication, or 2FA. It's built on a super simple principle. To prove you are who you say you are, you need something you know, that's your password, and something you have, that's a temporary code sent to your phone. Seriously, if you're not using it on your important accounts, you really should be. But there's a hidden cost to all this constant connectivity. The average person now checks their phone 96 times a day. That works out to roughly once every 10 minutes that you're awake. And believe me, this isn't an accident. The fact is, these platforms are engineered to be addictive, creating a constant battle for our attention. And this has real consequences for our focus and our mental well-being. And it's sparking some major debates in society. For instance, you've got countries like Norway that are completely re-examining the role of phones in schools because they're acknowledging their impact on concentration and learning. So, here we are at the end. We've traveled from 19th century equations to microscopic switches, all the way to a global network that is actively, and very successfully, engineered to capture your focus. Understanding how it all works, well, that's the first step. The next step is a question that only you can answer. In this world that is built for your attention, how will you choose to spend it?